I'm going to work through some of the, or all of the homework problems that were assigned for pages 172 and 173 on implicit differentiation. So let's jump in and take a look at the first problem. We are to use implicit differentiation. Let's change colors here. To find an equation of the tangent line. So always identify what your goal is. In this case, our goal is to find the equation of a tangent line. So I'm going to write down my target. Y minus y1 is equal to m times x minus x1. So that's my goal, and in order to write the equation of the tangent line, I'm going to need an x1, a point, and a y1. So I'm going to need a point. And I'm going to need slope, which is the derivative at the given point of 1, 2. So they've already given me a point, so that's kind of nice. They've already done a lot of my work for me. So far I can go ahead and substitute y minus, the y value is 2, is equal to, the slope I do not know yet, equal to x minus 1, the x value. So what I have to find is the slope, so I'm going to need the derivative. So I'm going to do that over here on the right hand side. So the function, it might be helpful to rewrite this as 1/2 x squared plus 1/8 y squared. Sometimes getting that coefficient or that fraction off, or the denominators from underneath the x squared and y squared, helps students to see what to do better. So when I take the derivative implicitly with respect to x, the derivative of the first term will be x, because 2 times 1/2 is 1, decrease the power by 1, that's just power rule. And for the second term, 2 times 1/8 is 1/4, decrease the power by 1, and then leave the chain rule, dy dx. The derivative of 1 is 0. Now I'm going to get the dy dx by itself because my goal is to find the derivative. So I'm going to subtract x from both sides, so there's that. And then I'm going to divide both sides by 1/4 y. So dividing by 1/4 is the same thing as multiplying by 4. And that'll be over y because we're dividing. And so my slope generator is negative 4x over y. So I'm going to need to substitute the x value of 1 in place of x and the y value of 2 in place of y. So dy dx at the point 1, 2, substituting 1 in place of x will give me negative 4 in the numerator. Substituting 2 into the denominator will give me 2. Negative 4 divided by 2 is negative 2. So now I have my slope, so I can substitute that back over here into the equation of my tangent line. And then the last thing I'm going to do is to get y by itself, so I'll do that over here on the left hand side. So I'm going to add 2 to the right hand side. That'll give me negative 2 times x minus 1 plus 2. So that is the equation of the line tangent to that ellipse. So I paused the video for a second and I went over to Desmos and I actually graphed what we just did. So I think it's always helpful to see a visual of what's going on. So what I did was, let me grab my pen here and change that to a color. So I graphed this ellipse right here, as you can see right over here. So there's the ellipse. And then I graphed the tangent line that I created right here, or actually this one right here, to where y is by itself. And you can see that that line is tangent to the curve at the point 1, 2, which is exactly what we wanted to have happen there. So I think it's always good to have a visual to understand that we're not just doing procedure, there's actually a visualization of what's going on. So that's that implicit relationship, the tangent line, and the curve. All right, so let's move on. The next problem is number 59. I'm going to get rid of all this stuff and reset. So in number 59, let's see what we're doing here. Find the equation of the tangent line. All right, so there's one job. And the normal line. All right, there's two jobs. So we're writing the equation of two different lines. One is tangent, one is normal. The normal line, as you can see right here, is perpendicular to the tangent line. All right, so I'm going to pause that actually and create. I'm going to pause this video, not that it matters to you, and create that graph. And we're going to look at the visual first, and then we're going to come back and actually do the work. So over here to the right, you can see that we have a circle, because x squared plus y squared equals 25 is certainly going to create a circle. We know that. And then the tangent line, which is this line right here. This is the tangent line. You can clearly see that that line that we're going to actually produce here in just a second is tangent. And then the normal line, if you look right here in red, this is the normal line. This line is, you can see visually, is perpendicular to the tangent line, and that's what a normal line is. So there's our perpendicular, those are our perpendicular lines. That's actually what we are about to create and find. So let me move that graph out of my way, or maybe I'll just make it smaller, keep it up here as we do our work. So let's get rid of that. Let's put it up here and get rid of these guys. Okay, so in number 59 in blue, we're going to have the equation of a tangent line. So whoops, that's not blue, so let's go back to blue. So y minus y1 is equal to m times x minus x1. So same kind of job we had in the first problem. And then we're going to write the equation of a normal line in red. Y minus y1 is equal to m times x minus x1. So we need the same things. And in this case, we're doing two different points. I just did one point up here in the graph. Let's see, which one did I grab? I did the positive point 4, 3. So we're writing the equation of 4 lines because we have two different points. The one that I showed you was at 4, 3. So let's start our tangent line. We have y minus 3, substituting the y value, I don't know the slope yet, is equal to m times x minus 4. That would be the tangent line whenever I find the slope. And then the equation of the normal line would also be y minus 3 equal to x minus 4, and that's going to be the normal line. Now remember, perpendicular lines have opposite, meaning change the sign, reciprocal, meaning flip, slopes. Opposite, reciprocal, slopes. So once I find the slope of the tangent line, I will basically almost already have the slope of the normal line because it's opposite reciprocal slopes. So to find my slope generator, I'm going to come over here on the side and I'm going to do implicit differentiation. So the derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x is 2y. There's my chain, dy dx, equal to 0. Derivative of constant 0. dy dx, my slope generator, I'm going to subtract 2x from both sides and divide by 2y. So my slope generator is negative x over y. So the derivative, or the slope of the tangent line at the point 4, 3 is going to be opposite of 4 over 3. So I'm going to come back over here and almost complete my tangent line. So that's negative 4 over 3. And then we said that perpendicular lines have opposite reciprocal slopes. So the opposite of negative 4/3 is positive 4/3, and the reciprocal of 4/3 is 3/4. And then to finish up the equations of my line, I'm going to have y equal to, remember, always get y by itself, negative 4/3 times x minus 4 plus 3, and then the same thing for the normal line. I'm not going to rewrite that one, but just make sure that you get y by itself. Whether you distribute, combine like terms, I don't really care at this point. Now the only difference when we go to the other point of negative 3/4, so the only difference, I'm not going to write all these equations up. You can use the solutions manual to check all of that, but the only difference is negative 3 over 4. So the derivative, or the slope of the tangent line at negative 3 over 4, substituting into the slope generator will be the opposite of -3 is 3 over 4. So the slope would be 3/4 and the point would be, what are we doing? -3/4. So y minus 4 is equal to 3/4 times x plus 3. And then the equation of the normal line would be the same, except the slope would be -4 over 3 because perpendicular lines have opposite reciprocal slopes. And I'm not going to do number 60 because 59 and 60 are basically the same problem with different numbers in them. And I'm seeing that number, we're not supposed to do number 60 anyway, so that works out nicely. So let's go back to the top, clear the screen, and the next item that I have selected is number 63. So in this case, we are finding the points at which the graph of the equation has vertical and horizontal tangent lines. So goal here is vertical and horizontal tangent lines. So let's take a look at the graph of this thing just to visually see whether or not this thing is going to have vertical or horizontal tangent lines. So if you look over here to the left, I have brought the graph of this ellipse in, and we're looking for vertical and horizontal tangents. And we can see that there are two vertical tangents, one over here on this side, I'm writing in blue, and one over here on this side. So two vertical tangents and two horizontal tangents. So visually we can see, yes, this graph is going to have vertical and horizontal tangents. So to find vertical tangents, well, the first thing we're going to have to do is find the derivative of this expression. So in number 63, I'm gonna start the derivative work up here. The derivative of 25x squared with respect to x, well, already messed up. Let's erase that. Derivative of 25x squared is 50x, and the derivative of 16y squared is 32y. Chain rule, dy dx plus 200 minus 160. Chain rule, dy dx. I'm taking the derivative of y term. The derivative of 400 is 0, and that's equal to 0. So my slope generator, dy dx, is equal to, I'm going to subtract the 50 and the 200 to the right-hand side, so that would be negative 50x minus 200 divided by, I'm going to put the dy terms together on one side, factor, and then divide by 32y minus 160. Okay, and you should actually show that work more slowly than what I'm doing. I'm just actually going to double check myself to make sure I did not make a mistake before I move on. Okay, so that is correct, and so let's think about, we're finding vertical. Let's start with vertical tangents. Vertical tangent, remember a vertical line looks like that, and the slope of a vertical line is undefined. Therefore, that means we're trying to set the denominator equal to 0, because that's how you make the fraction go undefined. Try to divide by 0. So I'm going to set 32y minus 160 equal to 0. So I'm going to add 160 to both sides and divide both sides by 32. And that'll give me a y value of 5. So for the vertical tangents, vertical, I know that I have something 5 because I have the y value. To find the x value or x values, because we've already looked at the graph, we actually know that there are 2. We're going to substitute the 5 back into the original equation, which is down here. All right, so when I substitute using I would certainly use calculator here, but I would have 25x squared, and then 25, I'm using my calculator, times 16 gives me 400. I'm substituting into here, so that's going to be 400 when I substitute 5. I substituted 5, squared it, multiplied by 16, plus 200x minus substituting 5, 160 times 5 gives me 800 minus 800 plus 400 equals to 0. All right, so I'm going to take the 400 and add it to the 400 and get 800, subtract 800, so these are going to be gone, and that's going to give me 25x squared plus 200x equal to 0. I can factor out 25, and that will give me x squared plus 8, because 8 quarters make $2. I was factoring out an x. Let's try that again. Erase, erase, erase. There we go. All right, so we're going to factor out a 25x. That leaves me with x plus 8 equals 0. Set each factor equal to 0 by the zero product property. And x is equal to 0, or x is equal to negative 8. So I have a vertical tangent at 0, 5, and I have a vertical tangent at negative 8, 5. And if we come over here to the graph, this is actually 0, 5 right here. And on the other side, this is negative 8, 5 right here. So graphically that works out. And so that supports my answer. All right. So let's change colors. Let's go to a white over here. So on the right-hand side, now I'm going to look for my horizontal tangents. So to get the horizontal tangents, remember a horizontal line looks like that and has a slope of 0. So we're going to set the numerator equal to 0. So that'll give me, from my slope generator, negative 50x minus 200 equals 0. I'm going to add 200 to both sides and divide by negative 50. And so 200 divided by negative 50 will give me negative 4. So I have an x value of negative 4. And an x value, I know that there are 2 already because visually, and we can see over here, if you look at our graph that we produced at negative 4, that's where we're expecting the x value to be. And to get the y values that correspond with those, I'm not going to do that right now in the interest of time because it's the same procedure, but I would substitute the negative 4 back into the original function in place of x. Carefully do my arithmetic. Probably use a little calculator, and I can actually see, can I see that one of the y values is, that I can just see from the graph, that we would not normally have, is 0, and the other one is at 10, so you can check your work to make sure that is correct. All right, what do we have up here next? 64. Not going to do 64 because 63 and 64 are basically the same problem, and 63 actually has bigger numbers, so I did the one that would be, quote, considered more difficult. Let's take a look at number 65 and see what's different there. I'm going to get rid of this graph because I don't think we're going to need that anymore. 65, okay, 65 and 7. Some good old logarithmic differentiation. Let me create a little more space here. Boom, boom, boom. So number 65, I'll do this one over here on the left-hand side. Let me copy that problem and just start it from scratch. So number 65, I'm going to go ahead and take the ln of both sides because we're going to do logarithmic differentiation, so that'll give me the ln of y on the left side. On the right side, I'll have the ln of x times x squared minus 1 to the 1/2 power. So the first thing I'm noticing with my math eyes, there are my math eyes, is I see a product, so I can use log properties to rewrite that. That's why we're doing the logarithmic differentiation, to make the problem much easier. I can change that into ln of x plus, and I'm going to use the power property, bring down the 1/2, ln of x squared minus 1. So using those log properties makes things much easier. Now I'm going to go to the calculus phase. The derivative of the ln of y is dy whoops. Let's go ahead and write it that way. Change, erase, ln, I forgot we were doing ln. The derivative of the ln of y, let's try that again, is y prime over y. The derivative of ln of x is 1 over x. 1/2 is a coefficient, so I'm going to leave that out front. The derivative of ln of u is u prime over u, so I get 2x over x squared minus 1. As far as cleaning, I can divide this 2 with this 2. Next step, I'm going to get y prime by itself. So y prime is equal to 1 over x plus x over x squared minus 1, multiplying the y to the right-hand side. And then the last step is to resubstitute the original function. So x over x squared minus 1 times y, which is x times the square root of x squared minus 1. Now, if you decide to go to the solutions manual, I assure you that it's going to clean a whole lot more than I did, but this is perfectly fine. And then lastly, I already forgot what number it was. Let me make sure I do the right number. Number 67. So I'm going to do that one right here on the paper. So number 67, I'm going to take the ln of both sides. So I have the ln of y. On the right-hand side, I see right here a product and a quotient and power. So I'm going to use lots of log properties. So the first property, I'm going to split up that numerator and make that 2 ln of x, because I can use a power property on that. Here comes the multiplication, so that's plus. I'm going to use the power property, bring the 1/2 power, which is the square root, out front. ln of 3x minus 2. All right, so that takes care of the numerator. I did the multiplication and I did the powers. Now in the denominator, since I'm dividing, I have subtraction. I can use the power property to bring the 1/2, which is the square root, out front. ln of x plus 1. On the left-hand side, the derivative of ln of y is y prime over y. On the right-hand side, the derivative of ln of x is 1 over x, so that gives me 2 over x. The derivative of ln of u is u prime over u, so I have a coefficient of 1/2. U prime is 3 over 3x minus 2 minus coefficient of 1/2. The derivative of, here's u prime over u again, so I have 1 over x plus 1. As far as cleaning, we're going to have the y prime equal to, I have 2 over x plus, nothing reduces in this second term, so I'm just going to distribute the 2 into the parentheses and make that 3 over 6x minus 4. No, you cannot divide the 3 and the 6. That would be a big no-no. Last term, I can't divide the 1/2 with anything, so I'm going to distribute the 2 into the denominator and make that 2x plus 2. And then I'm going to multiply by the y, and the original y is x squared times the square root of 3x minus 2 over x minus 1 squared. It's ugly, but I think it's right. I don't think I made any mistakes in there. So that's the first part of your homework, and I'm going to do a video for the next part of your homework as well.